everyone, welcome to part 3 of chapter 19. Today we are going to pick up where we left off last time in calculating the E0 for the cell for spontaneous redox reactions, right? Those are voltaic cells. So now we're going to use that calculation and relate it to delta G, which we've calculated before, and we're also going to calculate K. So we're going to relate all three of these variables. Then we're going to look at how do we calculate the E of the cell for non-standard conditions, right? What if the concentrations aren't 1 molar? And we're going to look at concentration cells, which is when the anode and the cathode are made up of the same material, and the reason that electrons flow is because they have different concentrations. And then finally, we're going to wrap up, we're going to talk about batteries and fuel cells. So lots to cover today, so let's get going. All right, so the first bit we're going to talk about is relating our E0 of the cell, right, our electromotive force of the cell, to our delta G value, that Gibbs free energy, and K, which is our equilibrium constant. And we know for a spontaneous reaction, right, one that goes in the forward direction, for all of these, we know that E is going to be positive. That's what we've been talking about thus far. And in the last chapter, we talked about the fact that delta G needs to be negative for spontaneous reactions. And we know that K needs to be a really large number in order to say that the forward reaction is favored. So these are our three conditions for saying, the reaction goes to the right, essentially. And so now we're going to have a new equation. So our Gibbs free energy equation, this is a new one. So it's going to be delta G is equal to our negative N, which is the number of electrons that are being transferred. And we'll look at how to see that a little bit later. And then F is Faraday's constant. So that is 96,485 coulombs per mole of electron. So that's the amount of charge we're getting for each of those electrons that are being transferred, right? Based on the number of N. And then times the E0 of the cell, which we've looked at how to calculate thus far. So now that we can calculate that, we can calculate delta G, and we can also see, whether it's spontaneous. And remember, delta G is telling us how much work can be done by our system, which is related to the amount of volts that can be transferred. All right, so let's go ahead and try this out. So we're going to calculate delta G for this reaction below. And we know that we're going to use this equation, okay? So in order to use this equation, we will need to calculate our E0 of the cell. And we've already done that before, right? We're going to look up our reduction potentials for both of them. And remember, we're going to flip the one for oxidation. So here, bromine is being oxidized. It's losing an electron. So we would look up the reduction potential and then make that negative, so it's oxidation. And then we would look up the reduction potential for our iodine reaction. And then we can just make sure our electrons cancel and add them together. So now what's important here is we've always been calculating it in volts, but volts, another way of writing volts is joules per coulomb. That's the definition of volts. And the reason that that's useful is that when we use this equation, right, our Faraday's constant has coulombs in it. And in order to see how all of the units cancel, we need to change this to joules per coulomb. So as you can see, right, when we have joules per coulomb now, our coulombs can cancel, our moles of electrons are going to cancel, and we'll end up with joules when we're playing with our units here. But let's go through this. So delta G is equal to negative N, so 2 moles of electron. That's here. Remember when we make our electrons equal? So the number of electrons that we end up being, lost and gained during this reaction, that's our N value. So that would be 2 because our bromine reaction is losing those 2 electrons and they're being picked up by the iodine. And then we have that 96,485, that is the Faraday's constant, and then our voltage, right, in joules per coulomb. So when we cancel out all our units, we get joules, and I've converted it into kilojoules here because most times we'll report our Gibbs free energy in kilojoules. So delta G is positive. So that means our reaction is not spontaneous in the forward direction under standard conditions. But we would know that already looking at our E0 value, right? Our E0 value is negative. And for a spontaneous reaction, we need it to be positive. So both of these two things are telling us that this reaction is not spontaneous in the forward direction, but it would be spontaneous in the reverse. So I want you to go ahead and try one. Do it just like we just did. And you've got a little bit more of a complex reaction, but you can use these half reactions below to figure out what you need. So go ahead, pause here, calculate delta G0 just the way we did before, and when you're ready, unpause and I will go over the answer. go through this. So calculate delta G naught for that reaction at 25 degrees Celsius, so standard conditions. So again, we're going to use this Faraday's equation. Okay, and the first thing we need to do is solve for E naught of the cell. So we would look on that table and we would find things that match up, right? We are seeing that our iodine is being oxidized. So our iodine is going from I- to I2, right? And it's also being reduced from iodate to I2. Okay, so both of those two reactions, when we combine them together, we'll get our overall reaction. Now, previously when we used this reaction, I told you it didn't matter really how they were balancing out, but now it does because we need to see how the electrons are canceling, right? So in our reduction reaction, we're seeing 10 electrons. So we can just multiply our oxidation reaction by 5, and then we'll get 10 electrons and they'll cancel out. And the reason that we need to know how many electrons are in that transfer is because we need this N value. Okay. Remember again, when we multiply our reactions, like say the first reaction got multiplied by 5, remember we are not multiplying our E naught value because our E naught value is an intrinsic value. Okay, so we don't multiply, an intensive value, we don't multiply that number by anything. Okay, so now we've got delta G naught is equal to our negative N times F and E naught of the cell. So we can go ahead and plug things in. So 10 moles of electrons are being transferred. And then we have our Faraday's constant. And then remember, we're using our volts as joules per coulomb to make sure that our units are all canceling. And this will spit out delta G in joules. And then we can convert it to kilojoules just because that's how we normally report delta G naught. And then this is negative, right? So that tells us that our reaction is spontaneous in the forward direction. And we would know that also by looking at our E naught of the cell. That's 0.66 volts, which again is positive. So that's telling us that this is a spontaneous reaction. Okay, so as you saw on the previous slide, we can relate E naught to delta G, but we can also relate E naught to K because we know that we can relate delta G to K. On the previous slide, we had delta G is equal to negative NF E naught of the cell, right? So we can put those together because we also know delta G is equal to negative RT times the natural log of K. So if we cut delta G out of the middle here, we can set those equal to each other and we can rearrange and solve for E naught of the cell. Okay, so E naught of the cell is equal to RT over NF times natural log of K. And some of those are constants, right? R is a constant. We know 8.314 joules per mole Kelvin. We know temperature at standard conditions is always going to be 298.15 Kelvin. Our number of moles will change, but Faraday's constant is always going to be that 96,485. So if we wrap, this and our temperature at, 25 degrees Celsius, if we wrap all those three together, we get 0.0592 volts. So at standard conditions, we can use E naught of the cell is equal to 0.0592 volts over N times log K, which is easier to use. But if you're ever at a different temperature, then you're going to need to use this one. 99% of the time in this class, this will be the equation that you use. All right, so calculate K at 25 degrees Celsius for the reaction there. So again, we need E naught of the cell just like we needed before, and we need to see how many electrons are being transferred in this reaction in order to calculate K. So first thing we're going to do is solve for E naught of the cell. We'll look at our oxidation reaction. Again, remember, you're going to take your reduction potential and make it negative to make it oxidation. And then we have our reduction reaction. Hydrogen is 0, right? That's why we use that standard hydrogen electrode at 0. So when we add these together, it's just going to be the voltage from that copper reaction. Okay. So now we can plug things in. So I've rearranged my equation already, right? I multiplied both sides by N divided by 0.0592 so that I could get log K by itself. So I can plug things in here. And you'll get that log K is equal to negative 11.5, or rounding for significant figures, negative 12. Okay, and then to get rid of the log, remember you always do, 10 to the log, right? And so we're doing 10 to the negative 11.5. And then I've rounded my final answer, though, for the proper significant figures, 3.2 times 10 to the minus 12. Okay. And so if we look at our E naught value is negative, which tells us that this is not a spontaneous reaction. It doesn't really proceed in the forward reaction. And that is also what K is telling us, right? K is really small, really small, right? Times 10 to the minus 12. That's telling us our reaction does not go very far in the forward direction. So it may go a little bit, but it is a reactant favored reaction. So we can see that from E naught. We can also see that from K. All right, I want you guys to try this out. This is the same reaction we were using previously. So go ahead, pause here. You should already have calculated E naught of the cell in the last time, but you can just use that now to calculate K. All right, let's go over this. So again, we're going to use this equation. And so we already have solved for E naught of the cell. We made sure our electrons cancel, all that good stuff. But now we can just go ahead and plug it in. Again, I've already rearranged my equation here. So I can plug in our E naught value, our N value, right, which is 10 moles of electrons, and divided by 0.0592 volts. And that'll give us 110. And then we do times 10 to the on each side to get rid of that log. And we'll get 10 to the 110th. So, I mean, that's a pretty big K value, right? A really big K value, which is telling us that the equilibrium lies really far to the right under standard conditions. So that reaction is product favored. So it will proceed in the forward direction, which again, we were seeing from E naught because that is a positive value. That's also telling us that it's going to be spontaneous in the forward direction. Okay, so moving off of that, right? We've talked about how to calculate delta G naught and how do we calculate K, both from E naught of the cell. So now we're going to take what we've learned, and all of those were always at standard conditions. When everything was 1 molar, all gases were 1 atm, right? Everything was standard conditions. Now we're going to look at what happens when the ion concentrations are not 1 molar, okay? And we know from our previous chapters that there's a relationship between the reaction quotient Q and the equilibrium constant K and the free energy change delta G. Remember, so we said delta G naught was when it was at standard conditions, and we could calculate delta G when it wasn't, right? When we had different conditions, different concentrations. So we can do the same thing here. Changing the concentrations of the reactants and products so that they are not 1 molar affects that standard free energy change delta G naught. Again, we calculated delta G. So the same thing here, right? So instead of having instead of having E naught of the cell, we're just going to have E of the cell, which will tell us that it is not standard conditions. Okay. So let's look at this. So our cell on the left is at standard conditions. So we would just use the reduction table in the back. And we would look at, we would have our zinc reduction potential, but we'd flip it because it's oxidation. And then we would add that to the reduction potential for copper, and we would get 1.10 volts. Okay. When it's not at standard conditions, right, we've changed the concentration. So this is the only thing that's changed here, is that our zinc concentration, we have decreased our zinc concentration, and we have increased our copper concentration. And so when we do that, we are changing the voltage, right? So it's no longer at standard conditions. It will be something different. It will either be greater than or less than the standard conditions, but it won't be the same. And so we're going to go through how do we calculate that. Okay, so the first equation should look really familiar. That was from the last chapter, right? Delta G is equal to delta G naught plus RT natural log of Q. But we can change this and use it for our E values. Okay, so I've substituted in, and so now we can get E is equal to E naught of the cell minus RT over NF natural log of Q. But again, I'm going to combine all these together just to make our lives easier, and then I'm going to change our natural log to log, so we can get this same 0.0592 volts like we were using before over N times log Q. Okay, and so that will be how we relate E of the cell, right? So at non-standard conditions, so we'll do E naught of the cell. So standard conditions, just like we would use with the reduction potentials, and then you would calculate Q based on your different concentrations, and that would get us E of the cell. This equation is known as the Nernst equation, and it just allows us to determine the cell potential at non-standard conditions. Okay, so here I've broken it back down again, so this will be at standard conditions down here. But at the top, this is just for general, any temperature, right? When we have Q is less than 1, So if we have Q is less than 1, remember Q is products raised to the power of their coefficients over reactants raised to the power of their coefficients, okay? So if Q is less than 1, that means we have too many reactants, right? We have a lot of reactants, not very much product. When we take the natural log of Q, that will make it negative. And so this will be negative times this negative, which will make it being essentially a positive number. So E naught of the cell plus something will give us E of the cell will be greater than E naught of the cell. And then I'm going to skip the second bullet point for a second, but when we have Q is greater than 1, that means that we have a lot of products. And so when Q is a very large number, we take the natural log of that, it will be greater than 0. So we'll end up having E naught of the cell minus something. So E of the cell will be smaller than E naught of the cell. Okay, so but when Q is equal to 1, so when Q is equal to 1, our reactants and our products are equal in concentration, which means that Q is 0. And when we take the natural log when we take the natural log of 1, that whole thing goes to 0, and if we multiply 0 times RT over negative NF, right, then that all will be 0 as well, which will tell us that E of the cell is equal to E naught of the cell. So that's happening when our reactants and our products are equal. And then finally, when Q is equal to K, right, that's telling us we are at equilibrium. And when we're at equilibrium, right, all of the electrons that are being transferred one way are also being transferred the other way. So there's not this net transfer of electrons, and we need a net transfer of electrons in order to have some electricity, right? So if we don't have a net transfer of electrons, then E of the cell will be equal to 0. Okay. All right, let's go ahead and try this out. So we have E of the cell at 25 degrees Celsius for the reaction below. And we want to know when copper is at 0.01 molar, our permanganate is at 2.0 molar, and then our hydrogen ion is at 1.0 molar, right? So our hydrogen is, essentially still standard conditions, but everything else has changed. Okay, so the first thing we need to do is go through and calculate E naught of the cell. That's like 9 times out of 10, whenever you're given a problem in this chapter, go through, calculate E naught of the cell, because you're probably going to do something with it. So let's do that first. So our oxidation, right? Our copper is being oxidized because it is losing electrons. So we'll get that copper reaction. Remember, we're going to make our reduction potential negative to make it oxidation. And then there's our reduction reaction. And we need to make sure our electrons cancel. So we have 3 electrons and 2 electrons. We'll make them both go to 6. So we'll multiply the top one by 3, bottom one by 2, and then we can add our reactions together. Okay. Again, remember, when you're multiplying your reactions by a number, don't multiply E naught by anything. So there we go. There's our E naught value, our E naught of the cell, and now we can plug that into our equation, right? We're going to need to solve for Q. So when we solve for Q, remember, it's always products over reactants raised to the power of their coefficients. So here we go. So we have products, right? We don't include our solids. Remember, we don't include our pure liquids. So the only thing on the right is going to be copper. So copper will be raised to the power of its coefficient. That's a 3. Over, we have our permanganate squared and our hydrogen ion to the 8th. Okay, and then you can plug all those numbers in with their molarities and calculate the Q value. I do want to pause here just before I forget. When you're calculating Q, here all of our reactants are aqueous that we are including, right? We're not including solids, we're not including liquids, but we would include gases if they were here. And so if you come across a problem where you have both aqueous concentrations and partial pressures from gases, if your partial pressure is in ATM, you can use it in the Q calculation just the same as you would molarity. So you're just going to include it just with all the molarities. So if you have molarities and you have pressures in ATMs, you can put them in the same equation and go through and calculate it. That will be important to you at some point. So just make a mental note of that. Okay, back to this though. So we've plugged in our molarities, calculated Q, and now we can go ahead and plug that in and solve for E of the cell. So we have our E naught value, which we're going to plug in here. And then we've got minus 0.0592 over 6. Remember, 6 electrons are being lost and gained. And then we've calculated our Q from above. So when you calculate that, you get E naught of the cell is 1.41 volts. Okay, just like we expected, E of the cell is going to be greater than E naught of the cell because our permanganate ion is larger than 1 molar and our copper ion is smaller. Okay, so that's what we were talking about before with the products over reactants. Here we have a lot of reactants, which will make our Q value, small. So when we take the log of that, it's making a negative number. So when we add it together, we're getting larger than our E naught of the cell. All right, go ahead and practice this. So it says calculate the E naught of the E of the cell, sorry, not E naught, E of the cell for the reaction at 25 degrees Celsius if all of those ion concentrations are 0.1 molar. So go ahead, pause here, come back when you're ready. All right, so here we are. So first thing first, like I said, always calculate E naught of the cell first. We've used this one a couple times already, so there you go. And then you need to solve for Q, right? So Q is always going to be our products over our reactants raised to the power of the coefficients. So in this problem, we have a pure solid and a pure liquid as our products. So we don't have any products on the top, so we're just going to put a 1. So everything goes on the bottom now because all of our aqueous solutions are reactants. So you'll include them all there, again, raised to the power of their coefficients. So we're multiplying 0.1 together lots of times, and we're going to get 1 times 10 to the 24th. So a very, very large value for Q. So when we plug that in here, we've got our E naught of the cell, which we calculated, 10 moles of electrons, and a very large number for Q. And when we plug that in, our very large number for Q, that's going to give us a positive value coming out of the log, which means we're going to get E naught of the cell minus something. So just like we would expect, our E of the cell is smaller than E naught of the cell because our Q is so large, right? All of the ions are reactants. They're all less than 1 molar. So there you are. All right, our last bit on this non-standard condition, right? This kind of falls under that. It's concentration cells. So thus far, we've talked about what happens when our anode and our cathode are made out of different materials, right? Maybe our anode is oxygen and our cathode is aluminum, right? But it's something different. But what if they're the same? What if, say, both our anode and our cathode are made of zinc? Well, if the concentrations were the same, right, the concentrations were 1 molar, then the electrons wouldn't move. But if our concentrations are different, then we can get a spontaneous reaction from this concentration cells. Okay, and the difference in the energy is due to the entropic difference in the solutions. The more concentrated solution is going to have lower entropy because those molecules are all closer together, right? We can think of there are fewer microstates that they can exist in. So the more concentrated solution is going to have lower entropy than the less concentrated solution. And so then because of that difference in entropy, we're going to have a difference in energy, which means that we can have our electrons flow between those two solutions. So what we're going to do is calculate the cell potential using the Nernst equation to determine the direction of spontaneity in the cell. Just in general though, guys, the electrons are going to flow from the electrode in the less concentrated cell to the electrode in the more concentrated solution. Okay, and here's the reason why, right? So the oxidation of the electrode in the less concentrated solution will increase the ion concentration in that solution. Because remember, if we have a bar of zinc, well, when that zinc is being oxidized, it's going from solid zinc to zinc 2+, which means it goes into solution. This is going to dissolve, okay? And so when it does that, it will increase the ion concentration in that solution. Okay, so the oxidation is going to occur in the less concentrated solution, and the reduction will occur in the more concentrated solution because this one is going to plate out. Okay, so if you have, say zinc 2 plus in solution at the cathode, right, the reduction, it's going to grab some electrons and it's going to plate out. So what happens is it's going to, over time, decrease that concentration. So they're trying to essentially get to the same concentration. The one with the lower concentration will be oxidized, and the one with the greater ion concentration will be reduced, so that the one with the lower concentration increases its ion concentration, and the one with the higher one decreases its concentration. Okay, so again, when the cell concentrations are equal, there's no difference in energy between the half cells, no electrons are flowing. Okay, again, both of these are made from copper, and in both of these we have a 1 molar copper 2 plus solution. So the electrons don't have any reason to go anywhere, so they just kind of hang out. Okay, but when the cell concentrations are different, now we have electrons that are flowing. And again, the electrons are going to flow from the side with the less concentrated solution, okay? They're going to flow from the anode, less concentrated, to the cathode, which would be the more concentrated. So here, again, this one, right, is going to be our less concentrated solution. So we'll say that that's the anode. And then the one over here, this is more concentrated, so we're going to say that that is the cathode. And over time, the concentration of this solution will go up because that bar is going to dissolve as it becomes oxidized. And over time, the concentration here will go down because our solution is going to plate out. So the size of our bar would get bigger, right? But that blue color of our concentration would go down. All right, let's go ahead and try and calculate this. So we have a voltaic cell, which means it's spontaneous, right? It consists of 2 silver plus half cells. So that means on both sides, we have a silver bar, and on both sides, we're going to have a silver solution, a silver plus solution. In half cell A, the electrolyte is 0.01 molar silver nitrate. And then in half cell B, it's 4 times 10 to the minus 4th molar silver nitrate. And I want to know, what is E of the cell at 298.15 Kelvin, right? 25 degrees Celsius. So the first thing I would always do is draw yourself like a picture so that you see what's going on, okay? After that, let's logic through this, right? Remember that since we have a difference in concentration, the electrons are going to flow from the one that's lower in concentration to the one that's higher in concentration, okay? The standard half cell potentials in this reaction, right, because they're both silver to silver plus. So if we went through and calculated E naught of the cell, you would essentially get a number, and then you would subtract that number, and you would get 0. Okay, so E naught of the cell in concentration cells is always going to be 0 because the half reactions are the same. They're just flipped. Okay, so we're just going to calculate E of the cell without the whole E naught of the cell business. Again, half cell A has a higher concentration. Okay, so that means that is going to be our cathode. That is going to be reduced. Okay, they're going to plate out. In half cell B, we have a lower concentration, so that means that those silver atoms are going to be oxidized, and you're going to create Ag plus on that side, okay? Just the same, in all voltaic cells, reduction occurs at the cathode, so it's positive, oxidation occurs at the anode. So, as we go through this, our silver concentration will decrease in half cell A, because that is the one that's being reduced, right? So it's going to plate out. And it will increase in half cell B because our silver bar is going to dissolve and become silver plus. So we'll go ahead and we'll solve for Q. So we have our Q is going to be our products over our reactants, okay? So again, you need to make sure you have these going the right direction, okay? So we'll have products over reactants, so we'll get 0.040, and then we can go ahead and calculate E of the cell. So E of the cell is going to equal E naught, right, which we said is 0 because these are both silver reactions, 0.0592 volts over our number of electrons that are being transferred. Both of these are going from silver plus to simply silver, so that's 1 electron that's being transferred, and then we can plug in our Q value. And then we can get our E naught of the cell. So as you can see, it's kind of a small voltage, right? We're not getting a very large voltage out of this, but we are still getting some electricity going on, okay? So our application of this is a pH meter, like we used in our titration lab, right? The pH meter compares its internal hydrogen ion concentration to the hydrogen ion concentration in the solution. And so it's got these two different electrodes. It has a calomel electrode, which is our reference electrode, and it also has a glass electrode. And I don't need you to know a bunch about how this works. This is more just informational because I thought you would think it's relevant. So our glass electrode has an H plus concentration because it has hydrochloric acid in it. And so our solution would have some concentration of hydrogen ion, and it would essentially compare our hydrogen ion concentration in our solution to the hydrogen ion concentration in our glass electrode. And it'll go through this reference electrode, and here, this is essentially our salt bridge. It's got a porous ceramic plug that acts as our salt bridge. Okay, and so it's a concentration cell. It's looking at the difference in the concentrations of H plus and how much electricity flows because of that difference in concentration. So that's essentially what we were just looking at in our last example with the silver. So old school used to have two separate electrodes that you would stick in there. Now we just have the one electrode that is a combination electrode, but that's essentially what it's doing. It's measuring the hydrogen ion concentration in your solution compared to the hydrogen ion concentration in its solution, right, internally, and it looks at the electricity that flows to determine the concentration of your solution. Super cool. All right. Let's talk about applications of electrochemical processes. So thus far, we've talked about electrochemical cells, right? Essentially we set up two different beakers and we put a piece of metal in our beaker and we had some solution and we looked at the electricity that can flow from the beaker to the other beaker, essentially. But a battery works on these same principles, okay? So it's a voltaic cell, just like we've been talking about thus far, right? It's spontaneous, and it's arranged in series, and so it's a bunch of them, and it adds together all of the voltages from those voltaic cells, and it can use them to do work. Okay, we have two different types of batteries. One of them is a primary battery, and that means we can't recharge it. So essentially when our cell reaction reaches equilibrium, the charge kind of runs out and we consider the battery to be dead. The second type of battery, a secondary battery, is rechargeable. Okay, and so once you use up all of your stuff essentially that's being used to make the battery, you can input electrical energy and make it go the other way. Right? So instead of being a voltaic cell, you can make it act like an electrolytic cell, and you can make it go back and make those reactants again. And then the reaction can proceed just like it did before, and you can kind of keep doing that. All right, so let's talk about different types of batteries. I'm just going to talk about these briefly. This, again, is more informational, not something that I would likely test you on. Okay, so this is, for AA's, AAA's, these are alkaline batteries. So just so you understand a little bit how it works. So it's the same thing. You're going to have an anode, and you're going to have a cathode, and you're going to get some electricity out of it, right? It operates on all of the same principles that we've been using thus far. It just looks a little different than the beakers that we had set up, right? Because that would be a little bit ridiculous to use beakers in your radio or in your flashlight. So you have a zinc anode, right, which is on the inside, and then you've got some manganese dioxide in potassium hydroxide paste, and then you have a graphite rod, which acts as your cathode. Okay, and you have a bunch of other things that are going on. You've got a positive side and you've got a negative side, so you can get that electricity out, right, and complete the cell. So at the anode, we have our zinc is being oxidized, and at the cathode, we have our manganese is being reduced. Okay, so again, you could go through and calculate E naught of the cell and use that to see how much electricity you're generating. So we also have silver button batteries, and so they're like in your watch. So I hope this looks familiar to you so you know what I'm talking about. They're kind of flat batteries, and they're used in things that are usually a little bit smaller, right? But they still have the same kind of principle. So we have zinc is being oxidized, and we have our silver being reduced. And so you have our zinc, right? So our anode essentially is in potassium hydroxide gel so that it can react. And then you've got pellets of silver oxide, which are in graphite. That's going to act like the cathode. We've got a separator so they don't react till you want them to. And then you've got an anode cap. which is next to our anode, and our cathode can, which is touching our cathode. All kinds of good stuff. But again, the silver button batteries or the alkaline batteries we were just talking about, these are all redox reactions that are being used to produce electricity. These are single use, right? Once they run out of stuff, right? Once our reaction reaches equilibrium, then our battery is considered dead and it won't power whatever you wanted it to power in the first place. So you would, dispose of it how you properly should, probably not in the trash can, but however you should dispose of it, and then you would get a replacement battery. So a lead acid battery is a different type of battery. This is not your throwaway battery, right? A lead acid battery is the battery in your car, and it's a secondary battery, and it is rechargeable. So once it accumulates enough of the product, right, you can go ahead and input electricity, like from the alternator in your car, you can input electricity, and it will reverse the reaction and make your reactants again. Okay, so the way that this works is there are 6 different electrochemical cells that are in series, and each one of those produce 2 volts. So together you're getting 12 volts out of your car battery, which is pretty cool. Here, your cathode are going to be lead grids filled with lead 4 oxide, and your anode is going to have similar kind of grids, but they're filled with like a spongy little lead. And then you have sulfuric acid as your electrolyte, which allows the electrons to flow. So here's our reactions, just in case you're interested. At the anode, you have your lead is reacting with your hydrogen sulfite to make lead sulfate. And then your cathode, you have your lead 4 oxide is again reacting with hydrogen sulfate to make lead sulfate. Okay, so overall, you've got 2 different kinds of leads making lead sulfate, and you can reverse the reaction when you want to recharge it. All we've done is we've flipped it. Okay, so we've taken this reaction up here, lead sulfate and water, and now if I input electricity, I can make it make our lead 4 oxide and our lead and our sulfuric acid again so that we can use our battery again. So that's what's different from these secondary batteries, is that they are reversible. You can use an electrolytic process to get back your reactants so that you can use your battery again. Another application of this is the lithium-ion battery. It operates a little bit tricky, so we're actually not going to talk about how it reacts in this class. But essentially what happens is that the lithium migrates from the anode to the cathode through this electrolyte. Okay. But the reason that this lithium-ion battery is cool, it's a rechargeable battery. It's ones that are used in your computer. It has a really, really long life. It's super light. It's really environmentally friendly. And it's got great energy density, which means it gives off a lot of energy per gram. Okay, but again, it is a reversible reaction, right? So we can, recreate our reactants and use it again to produce electricity. So all of these batteries, right? We have to have reactants, that they're being used up, right? We have a finite amount that either we started with in our AA or our car battery, right? But the AA, when it runs out, we have to throw it away or dispose of it however you do. But when we use our car battery, right, we can use it up and then we have to recharge it with the alternator, or maybe you'll have to replace it eventually. Fuel cells, though, don't run out because the reactants are being constantly added. So you'll see this on the next page. So like hydrogen is continually being put in, oxygen is continually being put in. So it never runs down. So it can just keep producing electricity over and over and over again. The downside is that it's not self-contained. So like a battery, right, like a AA, you can stick it in your flashlight, you're good to go. You don't need to be attached to anything in order to produce that electricity. But the fuel cell, you'll need a constant input of hydrogen and a constant input of oxygen to make it go. So it's a definite downside. In this fuel cell, the anode and the cathode are both platinum-coated material because we've got that gas that's reacting. Our electrolyte is a hydroxide solution. Okay, so in both cases, we've got gases being put in. Okay, we have hydrogen and we have oxygen. And then our hydrogen will react with our hydroxide to make water, and it will produce electrons. So this is an oxidation reaction. And then our oxygen will use up those electrons with some water, and it will produce hydroxide, right? And again, you could see we could use, okay, here's our hydroxide, right? We produce some water, you can use it here, right? It's very sustainable. The only thing we need is we need to continually input hydrogen and oxygen to make this reaction go. Fuel cells are super cool. They're really clean, right? And they're used to provide electricity and drinkable water in space. How cool is that, right? If you've got some hydrogen and you've got some oxygen, you can make yourself some electricity. You can make yourself some water, right? It's really neat. But in order for these hydrogen-powered fuel cells to become more widely used, not just in space, we would need a more readily available source of hydrogen. Oxygen we have quite a bit of, right? We use it in hospitals and things like that, but hydrogen's not so readily available and it's not so cheap, so this would make it not as useful in that sense. But here's what it looks like. So on one side we would have hydrogen going in, on another side we have oxygen going in, right? And the hydrogen is going to be oxidized. So the hydrogen will find one of those hydroxide molecules and it will release an electron at the anode, right? And so we can use that electron can travel through, it can create some current, and it will travel to the cathode where it's going to be picked up by these oxygens and a water and create more hydroxide, right? And on and on and on. But it's really neat. Like I said, it's really clean. We have hydrogen and oxygen coming in. They're, producing water, they're using water, and we're just getting a really clean source of electricity. All right. That is the end of today's lecture. We covered a lot of ground. So again, we looked at the relationship between E naught, delta G naught, and K, right? We used that equation with the Faraday's constant. We also looked at how do we calculate E of the cell at non-standard conditions, right? Using that Nernst equation. And then we applied that to concentration cells where we made both the anode and the cathode out of the same material and looked at the flow of electrons just because of the difference in concentration. And then we looked a little bit at batteries and fuel cells and applications just in general of how we can use these voltaic reactions in order to do some work. So lots of practice today. Make sure you go through and look at that Chapter 19 lecture worksheet. That has lots of practice problems for you to do, so you get practice using the Nernst equation, so you get practice interrelating those three different variables, right? In the next lecture, we're going to wrap up Chapter 19 by talking about electrolytic cells. So thus far, we've talked about voltaic cells, which are spontaneous. Electrolytic cells are not spontaneous. We have to input energy in order to make these reactions happen. And you might think, what's the point of that, right? We've been using these reactions to get electricity out, like batteries. Why would you want to put electricity in? Well, guess you'll find out next time. So anyways, keep working hard, get lots of practice on those problems. If you have any questions, please send them my way. Otherwise, I will talk to you guys next time.